This lecture talks about torque on objects and how forces cause a torque to occur. The definition of torque is it's the magnitude of the force times the lever arm distance. The torque is positive when the force tends to produce a counterclockwise rotation about the axis, and torque is negative when the force tends to produce a clockwise rotation. And the units for torque are Newton meters. So in class tomorrow, remember that positive torque is counterclockwise and negative torque is clockwise. Here we have a door with three different situations. The same force is acting on all situations. And I want you to pause the video and decide which of these three situations causes the most torque. In other words, which of these three situations allows the door to open more easily. It is easier to open a door with a force of a given magnitude by A, pushing at the door's outer edge, than by pushing closer to the axis of rotation with the hinges. Pushing nearly into the hinge makes it very difficult to open the door. So the door A is the door that is the easiest to open. The door C is the most difficult. In this top view, the hinges of a door appear as a black dot and define the axis of rotation. The line of action and lever arm are illustrated for a force applied to the door. A is when it's perpendicularly, and B when it's at an angle. C, the lever arm is 0 because the line of action passes through the axis of rotation. So you always, this force here, it's the perpendicular distance from this force to the lever arm. So here's our lever arm, here's L. Now when we have our force at an angle along in door B, it's along an angle, but the perpendicular distance is not the length of the door. The perpendicular distance is this red line here. It's a different distance. That's why the torque is less, because it's line of action. You take this force here, this line along this force vector, that perpendicular distance to that line gives you your lever arm distance. And here, the force, the line of this force is right through the axis of rotation, therefore there is no torque. In figure 9.3, this is the figure below, the force whose magnitude is 55 newtons is applied to a door. However, the lever arms are different in the three parts of the drawing. A has a lever arm of 0.8, B is 0.6, and C equals 0. Find the magnitude of the torque in each case. So pause the video and go ahead and do that. The first one, you get a torque of 44 Newton meters. The second one is a torque of 33 Newton meters, force times lever arm distance. And the third one, the torque is 0 Newton meters. Now that we know the definition of torque and how torque acts, we're going to look at rigid objects that are in equilibrium. That means they're balanced. In other words, the sum of the torques add up to 0, and the sum of the forces add up to 0. The equilibrium of a rigid body is the definition here is what we want to talk about. It says a rigid body is in equilibrium if it has 0 translational acceleration. In other words, translational means along the line, and 0 angular acceleration, meaning that it's rotating. In equilibrium, the sum of the internally applied forces is 0. The sum of the in equilibrium, the sum of the externally applied forces is 0. And the sum of the externally applied torques is 0 as well. So in other words, the sum of the forces equals 0, and the sum of the torques equals 0 as well. So here we have some of the forces in the x direction add up to 0, the sum of the forces in the y direction add up to 0, and the sum of the torques add up to 0. So we're going to go ahead and look at this problem here. A woman whose weight is 530 newtons is poised at the right end of a diving board with a length of 3.9 meters. The board has negligible weight and is bolted down at the left end while being supported 1.4 meters away by a fulcrum, as figure 9.6 shows. Find the forces F1 and F2 that the bolt and the fulcrum respectively exert on the board. So we know that at the axis here, at this bolt, we have F1 down. At the fulcrum, we have a F2 pushing up, and the weight of the diver is down. Now we can pick anywhere to be our fulcrum, to be our pivot point, and they drew the fulcrum here, but we can put our axis of rotation right here. We can place that there, and that is where we measure our lever arms from. For example, F2 has a lever arm distance of 1.4, and the weight has a lever arm distance of 3.9. So we know that the sum of the forces add up to 0. That means negative F1 plus F2 minus W all add up to 0. Some of the torques have to add up to 0 as well. And since this is our lever arm here, we know that F2 times this lever arm distance 2 is in one direction, in the counterclockwise direction, in the positive direction. In the negative direction, we have the weight down times L sub W, which is 3.9 meters, this lever arm distance here. Those two add up to 0, or you can make those just equal and opposite. If we solve this second equation for F2, plug in our numbers, we know the weight of the person is 530 newtons. We know the lever arm distance here is 3.9 meters. And we know the lever arm distance down here is 1.4 meters. Gives us a force of 1,480 newtons is our F2 force. And now we can just use some of the forces. We can plug in our 1480 up here at F2. We know our weight is 530 newtons, and so now we can even solve for F1. That ends up being 950 newtons. This last problem is a fairly difficult problem. In figure 9.7a, an 8-meter ladder, weight 355 newtons, leans against a smooth vertical wall. The term smooth means that the wall can exert only a normal force directed perpendicular to the wall and cannot exert a frictional force parallel to it. It's smooth, there's no friction. A firefighter whose weight is 875 newtons stands 6.3 meters from the bottom of the ladder. Assume that the ladder's weight acts at the ladder's center and neglect the hose's weight. Find the forces that the wall and the ground exert on the ladder. So they want us to solve for push P here from the wall, and they want us to solve for this Gx and this Gy. Well, we have here's our picture of our fireman. We know the ground has a force in the x direction and in the y direction. The x direction to keep it from slipping, the y direction to build it up. The weight of the ladder is at the center of the ladder, straight down. The weight of the fireman is 6.3 meters up and straight down. We'll put our fulcrum right here at the bottom of the ladder, because at that point what will happen is when we do some torques, Gx and Gy will have 0 torque, so the only unknown when we do the torque equation will be the pushing force, and we'll be able to solve the problem from there. We have to remember we have to use vertical lever arm distances. It's not the distance along the ladder. In other words, we have 6.3 meters here up to the fireman. That's not our lever arm distance. Our lever arm distance is this horizontal distance. We'll have to use trigonometry. 6.3 meters times cosine of 50 to get the lever arm distance for the fireman. And for the ladder, we'll have to use the hypotenuse is 4 meters here for the ladder. So it'll be 4 meters times the cosine of 50 to get this horizontal distance, this lever arm distance for the ladder. Because see, the force line has to be perpendicular to the line to the fulcrum. So here's our axis of rotation. We know in the x direction that Gx minus P has to equal 0. Those two have to be equal and opposite. In the y direction, we have Gy minus the weight of the ladder minus the weight of the fireman, and they have to all add up to 0. And these equations actually go better with the picture before on the previous page. If you look at the picture on the previous page, you'll see that this picture here, that Gx and P are equal and opposite, and that Gy up has to be equal and opposite to WL and WF down. So that's what we have right here. Some of the forces in the X, some of the forces in the Y, And now we go ahead and actually we could solve for the weight of the ladder, the weight of the fireman, add those together, those two values. So we know that GY for the ground is 1,230 newtons. So that's the G in the Y direction. So now let's go ahead and solve for GX. And now we know from up here that GX has to equal P. We're going to use the torque equation to solve this. So we'll say the sum of the torques add up to 0. That means WL times its L, WL here times L, and WF times its L, its lever arm distance. Those negative torques have to be equal and opposite to this positive torque, this P times this lever arm distance here. Now if we go ahead and plug in and we solve for P and plug in our values, we have 355 newtons times that's the weight of the ladder. 4 times cosine 50, that's this distance right here. 875 is the weight of the fireman. 6.3 times cosine 50 is that distance right there. Divided by 8 times sine of 50, which is this distance right here. Because it's the vertical distance, so that's why they're using sine here instead of cosine. Gets 727 newtons. Well, if that's what P equals, then GX also equals that. So we have the GX is 727, and the GY we had from the previous page.